Yes, am I audible to all of you? Jasleen, Maniba, Jovita, Zainab. Okay. Class, in the last class, we stopped at this point. Mutual induction. We were discussing induction. So, what exactly is induction? Induction, we discussed that it's the property when the magnetic field changes, flux changes, and the current is induced. Now, when the current is induced within the same coil, then we call it as self-induction. When in the primary coil the magnetic field increases or decreases and the induced current occurs or induced EMF occurs in the neighboring, that is the secondary coil, we call it as mutual induction. So phi is equal to Li, that is equal to mutual L is equal to phi by I, that is the coefficient of self-induction, or you say it is self-inductance. And phi is equal to Mi, that is M is equal to phi by I, that M is the coefficient of mutual induction or mutual inductance. Okay. And both of them have the unit as Henry. This is what we discussed and we stopped at this point. Now the last part was left, just a very small topic. Let us start with then AC. Mutual inductance of two long solenoids. Now see, this is one solenoid. This is another solenoid. Now look, class, when you have two solenoids present, it's like both the solenoids are in very close proximity to each other. This is how the solenoids are placed. Now what happens is, each of the solenoid that we take, this solenoid and then this solenoid, each of the solenoid that we take will have its own primary, means it will have its own self-induction. But because two coils are present, then it will have a mutual induction also. So the way we calculated the same thing for the self-induction for a long solenoid, we are going to calculate the magnetic fields of two long solenoids as well here. So we'll assume R1 is the radius of the first coil, R2 is the radius of the second coil. And I1 is the current flowing through the first, I2 is the current flowing through the second, and both of them have the length L. Number of turns are given in both the coils. Now see, when we talk about one thing, when we talk about the mutual induction here, the flux, when we talk, see magnetic field, if I talk about the flux in this first coil, the magnetic field due to the second coil will be causing the induction here. The mutual induction, that is the current, induced current will be caused due to the neighboring coil. Now, if I'm calculating this is, let's say, the first coil, this orange one, which you can see, this is the first coil. And here, if I'm calculating its mutual induction, so mutual induction is coming due to which factor? It is coming due to change in the current here. So its magnetic flux is changing, its magnetic field is changing. That's why you're having a change in the flux here and you're getting a mutual induction. So when you write the formula here, phi 1, when you write, it should be equal to C. What is this? Flux is equal to B dot A. Okay, and if for n turns we'll multiply, flux will be equal to BA multiplied to this n. That is what has been written. Now for the first coil, for the first flux in the primary one, you'll write this as one, number of turns will be one, area of the coil will be the same. But magnetic field we will be considering as the second one. This will be the magnetic field of the second coil. Okay. And if we talk about the magnetic field of this, we should know its magnetic field using the Ampere circuit law. So for the solenoid, we already know the formula. B is equal to mu naught Ni. So for the second coil, mu naught N2 I2. See, what do we have here? If you have two coils, let's say there are two coils present. Okay. This coil is exerting a force on this. This coil's magnetic field is getting changed, due to which you have the induced current in this coil. So when I'm calculating everything for this coil, the magnetic field should be considered of this one, which is originating it. So its magnetic field is mu naught N2 I2 because it's a solenoid. So B2 is equal to mu naught N2 I2 is its magnetic field. Okay. And when we talk about the flux, the first flux, it will be B2AN1 because this magnetic field is being caused by the second one. So B2AN1 will be there, and B2's value we already know from the formula of a solenoid because these are solenoid, long solenoids. Long solenoids means infinitely long solenoids. So B2 mu naught N2 I2. Okay, this is one point. Now, when we talk about the mutual induction is also equal to flux divided by the current. Okay. Now I'm calculating the mutual induction on the first coil due to second, correct? Due to the second one, we are calculating everything, right? So flux, when you write no, phi is equal to mi. So when you are calculating on the first one, flux will be of the first, but the current that is getting changed due to which the magnetic field came, due to which this magnetic field, if this magnetic field is of the second coil, so we'll take the current also of the second coil. So using this, you will get this. Now this is one mutual induction. So let's put in the value of all the things. See, phi 1 will be equal to B2 is equal to mu naught into I2 into A into N1. Okay, this is the magnetic flux if we put in the value of the magnetic field. And from here, if I put the value of the magnetic field here as well, M12. So what will be M12 equal to? Mu naught N2 I2 A N1 divided by I2. See class, I2 gets cancelled. What do we get? M12 is equal to mu naught N2 A N1 divide. In fact, not divided, this denominator is getting cancelled. But one thing we can write here, N1 can be written as, see, number of turns. They can be written as N1 into N, that you can put in here. So M12 will be equal to mu naught A N1 N2 into L. This is how you get the mutual induction of both of them, and you don't get current. So even if I take the opposite, I'm just repeating what we have discussed, and if you have any doubt in this, then let me know, then I'll tell you for the next coil. See here, you have the magnetic flux for the first coil we are calculating. Okay, our target is this first coil. What is the magnetic flux on this first coil? The magnetic flux is equal to mi. Okay, we know this. Now see, when we talk about the magnetic field, yes, I was saying that when you are talking about the magnetic flux due to the first coil, the magnetic field of the second will be influencing it. So that's why the magnetic field that we see here is equal to B2, not B1. And one is there from the first coil. Flux 1 is there from the first coil. Both of them have the area same, so area A is given. But the value of B2 is going to come because magnetic field of the second coil is influencing it. Okay. Now for the second coil, you can write down the formula of B is equal to mu naught Ni. This is from the general formula of a solenoid, that is B is equal to mu naught N into I. If you use this formula and you multiply them, the whole value of the flux will be mu naught N2 I2 A into N1. This whole thing will come. Okay. Now we already know M12. Now pay attention to this. When you talk about flux, phi is equal to Mi. M1 will be there, phi 1 will be there, okay, because we are talking about the first coil. As I told you, we are talking about the first coil. But this current caused the second magnetic field, which caused the induced current ultimately, right? So if this is the case, then the current should be of the second coil, which is influencing. So that's why we just took I2 and we put in the values. And in fact, we put the values of this in also. Now, if you write the same thing, if I write phi 2, this will become B1, this will be N2, this will be N1, I1, this will be I1, this will be 2, 2. Means where you have 1, that will become 2. But eventually what will happen? That current will also be cancelled. I1, I1 will also be cancelled. That will also be cancelled. So ultimately you are still left with the same value. See, B1 is equal to mu naught N1I, phi 2 is equal to B1 AN2, right? Now see, B1 is equal to mu naught N1 I1. So we can say phi 2 is equal to mu naught N1 I1 A into N2. That is the flux in the second coil. Okay, that is the flux in the second coil. So M21 will be equal to the flux of the second coil, but the current of the first coil, because that is influencing your magnetic field. Okay, so flux 2 can be written as mu naught N1 I1 A by N2 divided by I1. I gets cancelled. So you get mu naught, and this is N1 A into N2. Now, what is N2 equal to? It is equal to small n2 into L. Now, see what are you getting M21 equal to? You're still getting this as mu naught. Am I audible to all of you?
Yes,
Is the voice breaking right now? Is it better? Please let me know in class if it is breaking or something. Is it fine? Muniba, Jesleen, now, Zainab. Muniba, you're there in the class? Am I audible to all of you? Yobita?
yes, ma'am.
Okay. Voice is breaking in between. All right. See, is it better now? Then I'll repeat it once.
Ma'am, can you repeat it?
Yes, I'm repeating. Yes, that's what I'm doing. See, you have two coils with you. I1 is the current across the first coil. Wherever the voice cracks or something, please just stop me so that it doesn't get messed away. I1 is the current through the first coil. I2 is the current through the second coil. They have their own radii, they have their own number of turns, and length is there. So what is done? Flux is calculated for the first coil. So magnetic field of the second coil is influencing its flux, right? The magnetic field of the second coil is basically influencing the first flux. That's what we studied in mutual induction. So phi 1 is equal to B2A N1. And B2 is the solenoid. So what is its formula? B2 is equal to mu naught N2 into I2. That is the formula of the solenoid. Okay, so when we write the mutual induction, the formula of the mutual induction is written as phi is equal to Mi. Now, M mutual induction of the first coil we are taking. Flux will also come of the first coil. But see, this was the current I2 which influenced its magnetic field. So I2 will be written not I1. So that's why phi 1 is equal to M1 I2 and phi 1 is also equal to this magnetic field's value here into An. Mu naught N2 I2 A by A into N1. When you put in the value, you divide it by I2, I2 gets cancelled. So you get mu naught into A N1. Now N1 can also be written as N small n1 into L because this is just the number of turns while small n is what? Number of turns per unit length, per unit length. So capital N. So what do we get as mutual induction? Mu naught N1 N2 A into. But if I write it for the same coil, if I write it as the magnetic field, that is equal to mu naught N1 I1. So flux 2 is equal to, now see, B1 will come because for the second coil, the first magnetic field is influencing. So phi 2 is equal to B1 AN2. So B1 is equal to mu naught N1 I1, same thing. When you put it here, M21 is equal to flux divided by the current, that is phi 2 divided by I1. So when you put in the value of phi 2 mu naught N1 I1 A N2 divided by I1, I1 still be cancelled. So you get mu naught N1 A into N2. Now N2 is equal to small n1 into L. So you get the same conclusion whether it is M12 or M21. You take any magnetic field and the neighboring flux will be influenced. That's it. This is all what you have to remember. Now tell me, have all of you understood this solenoid part or any part you want me to repeat? Jasleen, clear?
Yes, ma'am.
Zainab, did you get it? You said voice was breaking. Now is it fine? Did you get it? Okay, all right. Then please, all of you just write down this mutual induction part. One question we'll practice and then we'll move on. Yes, is it done?
Done, ma'am.
1 minute, ma'am.
Yes, if you increase the number of turns in the solenoid, the value of the mutual induction will also increase. With n, it will be increasing because your n2 and n1 will be influencing. So that will get increased. See, for the area will be simply pi r square. R for R1, R2, whatever coil you are taking, that area you have to consider. Okay. But you will get equal identical coils only, but you use that. Now there is one coefficient of coupling. Basically, this coefficient of coupling is a relationship. See, when two coils are there and they have mutual induction between them. So mutual induction is there. But within the coil, there is self-induction also. This part has self-induction as well. And between the coils, there is mutual induction. So coefficient of coupling is basically a constant term that connects all the three. So it is written as m under root L1 into L. That's it. Okay, there is one question. This says a solenoid of length 50 centimeter with 20 turns per centimeter and area of cross section as 40 centimeter square. Completes another coaxial solenoid of the same length whose area is given with 25 turns per centimeter. You have to calculate the mutual induction of the system. So M we have already talked of mu naught A N1 N2 into L. So from here M you have to identify. Mu naught you already know it is 4 pi into 10 to the power minus 7. Area of the coil that you're taking. So it's a mutual inductance of the system. This has given different cross-sectional areas for 40 centimeters square, 25 centimeters square. Now what you will do? You will take the lesser one. Because see, look, if I give a coil like this huge, this is a coil. And the second coil that is present is only taking this much of the area. Okay, like this. This is the coil which is present. Now look, the whole magnetic field that will be present will be within this region. The magnetic field cannot come in the region where the other coil is not present. That's why you take the lesser one. Their area, the mutual induction of both the coils will definitely there. But in this region, the mutual induction of both the coils will not be there. So we don't consider it. Okay, that's why when you take the mutual induction, you take the smaller one. So smaller area is 25 into 10 to the power minus 4 meters square. And one is given as 20 turns per unit length, right? 20 turns per centimeter it is given. Okay, so in 1 meter, if it's like in 1 centimeter, you have 20 turns. So in 10 to the power minus 2 meter, you have 20 turns. So when 1 meter, you have 20 into 10 to the power minus 2 turns. Like this, you have to calculate. Okay, so this will be, if we write this, N1 will be 20 into 10 to the power minus 2, while N2 will be, second length is, number of turns is, one was 20 of the same length, 25. So this will be 25 into 10 to the power minus 2. Length is 50 centimeters, so 50 into 10 to the power minus 2. You put all the data here, whatever you've got, all the data if you put, you will get the value of mutual induction, but in Henry. So will you be able to solve this question? M is equal to, using M is equal to mu naught N1 N2 into L. Is this fine?
Yes, ma'am.
Okay. Then write down this. This completes with the chapter. I'll start with AC then. Please write it. Done? Everybody has completed? Yes, others. Are you done except Moniba?
No, ma'am.
Jesslyn and Jobita, you both have completed?
Done, ma'am.
Oh. Yes, class. So the next chapter is alternating current. That is the chapter 7th of your NCRT. So, what is the difference between the current that we were studying and what is new about this current that we study, this alternating current? This is written as AC. Basically, when you have a direct current, there the current doesn't change with time. Okay, means if I have a fixed value of current, let's say this is 5 ampere. So throughout different time, 1 second, 2 second, 3 second, 4 seconds, I'll increase the time, the value will remain the same. See, whenever we did any question of current, we always had the current fixed. Like current in this circuit is 5 ampere, current in this circuit is 4 ampere, like this. We never had current is 4 sine theta omega and all. Like this, we never had a variable current. So that's what is known as the direct current DC. Means for every value, you're getting the same value of current. So that's how its graph is plotted. Then what's AC? AC means at every point the value will change. At every point the value will change. Look here. At 0, 1, 2, 3, 4, 5, 6, the value is continuously changing. And what kind of graph do you obtain? You obtain a sine graph or a cosine graph. Okay, you obtain a sine graph or a cosine graph. So current is variable. This is variable with the circuit. Okay. In your circuit, the current is constantly variable, and this is how we represent it with this symbol. Okay, this is how we represent a constant circuit. Now that represents the your alternating current, and direct current means the current's value will be fixed. Here at every point, the current's value will be changing. That's what you study in it. So we'll be talking about the AC generator or AC dynamo. Before that, you just write down this introductory part. Then I'll discuss AC generator with you. AC generator is similar to your EMI. So write down this first, then let's go into details of this chapter. Done, class? Okay then. So, talking about the AC generator or AC dynamo, basically what does it do is, it's a device that converts your mechanical energy, whatever is the mechanical energy of the system, into the electrical energy. This into the electrical energy. Okay. So it converts the mechanical. Now, how mechanical? Basically, in AC generator, the coil rotates. What is mechanical energy, by the way, class? Mechanical energy basically means kinetic energy plus potential energy together. That is what is known as mechanical energy. We did it in class 11th also. What's mechanical energy? Kinetic plus potential. So when the coil rotates, it is kinetic as well as potential. So mechanical energy is converted into electrical. Energies can change one form or the other. So mechanical energy basically gets converted into the electrical energy. That's how we get this. And what kind of electricity, what kind of electrical current is this? This is your alternating current. Okay. This one is the alternating current, AC. This is your alternating current. And it is completely based on the Faraday's laws of EMI. We just discussed the Faraday's laws of EMI recently. So this is based on the Faraday's laws of EMI. Okay. Whenever flux will change, EMF will get induced in the coil, whose formula is minus d phi over dt. Same thing will come. So in AC dynamo, what happens? Magnetic flux gets changed due to rotation of the coil in uniform magnetic field. It's like the question, remember, which I discussed in the last class also, and the one which Zainab you had the doubt in. The coil rotates. So this is similar to that. See, a coil is there. Coil will be rotating at various angles like this. So because of the change in the flux, change in the magnetic field, flux will change, due to which this mechanical energy will be used in the form of a current. That is the alternating current. And that current would be variable. It won't be a very constant value that you can obtain. That current will completely be variable. Okay. So I'll just tell you how it is constructed, how this coil is placed. Coil is a normal coil. Okay. The way you just have the wire turning, this is the coil that you have. Look, this part is the coil. While these are the permanent magnets present. These are the permanent north-south. These are proper permanent magnets present. And they have north and south both polarity in one end only. It's just that to represent, I have written one as north, other as south. You know, monopoles cannot exist. While this is the magnetic field which is passing from the north to the south. And here a coil is put, and this is assumed that the coil will rotate here across an axis with certain angular velocity, let's say omega, with certain angular velocity that is equal to omega. And this is basically the axis of rotation. Okay, this is the axis of rotation in which the coil would be rotating. And what are these, class, then? These are just slips which are connected. Okay. These are just circular slips that are connected. These are slips that are connected on an armature, so that the coil doesn't slip off. Okay, that's why it is present. Now, what will happen? We have already talked about magnetic flux. In magnetic flux, we take the area vector, that is n cap. And we know this area vector is always perpendicular. So see, magnetic field is fixed, but when the coil rotates, its area vector will change. Like, see, if this is its area vector, if it rotates like this, it would be like this. Then, if it rotates further, it will be like this. If it rotates like this, it will be. If it goes here back, it will be like this. The area vector means the perpendicular part will be rotating itself. So different angles would be there. Okay, you will get different angles over here. This theory part I'll tell later. First, let me discuss the construction. Permanent magnets are there. A coil is placed and it will be rotating over an axis. Angular velocity, let's say, is omega. Magnetic field is running from north to south. And various angles, how will we get? Angle will be formed between area vector and magnetic field, which we take in the flux. Flux is equal to BA cos theta. This is the same flux. So is this clear? Is this concept of AC generator clear to all? Yes. All right. Write it please then. From till here you all have written. Write it from here. Done? No, ma'am. Yes, now done. Yes. Okay. See, now the formula part is G quite here. See here, when you calculate the EMF, what have we discussed? The EMF's formula. When you write on, in fact, when we write the formula of the flux, we know flux is equal to BA cos theta, right? Now, this is equal to BA cos theta. That is the formula of the flux. So, when we have the EMF equation, it is minus d phi over dt, or in fact, I can say this is simply EMF is equal to flux divided by time. Minus sign is for the Lenz law, we already know. So flux from here, EMF can be written as flux, the whole flux divided by time, right? We can write this whole flux divided by time. In fact, I'll erase this. Okay, so this is equal to the flux. Now, if I put in the number of turns over here, so number of turns, n is the number. Yes, class. So see, I was discussing, yeah, EMF we have minus d phi over dt, right? For n, I was saying for n number of turns, we'll have flux as NBA cos theta. Now, if you put this equation, E is equal to minus d phi over dt. So for EMF, I'll have to write minus d phi over dt, which this minus d over dt of NBA cos theta is there. Now, look here, when you have cos theta, when it's cos theta is there, in a differentiation, when you write d cos theta, that gives you minus sine theta. So this will become, in turn, this will become minus. In fact, I'll just do one more step because here otherwise the constant term will go off. See, we know one more thing, that theta angular displacement, when you write angular displacement, can be written as the angular velocity into the time. So angular velocity is theta by t. So theta is written as omega into t. So from here we can write cos omega t, and this also becomes cos omega t. Why did I make this correction here? Because whenever you have any constant within the angle, so constant term comes out during the differentiation or integration part. In the differentiation, it comes out, means gets multiplied, and in integration, it gets divided. So this is differentiation. So this will be minus sine omega t, and there would be one more omega present over here. Okay, this will be minus omega sine omega t. So when you multiply, this gives you NBA omega sine omega t as the value of the EMF. Okay, now if I want to have the maximum value means sine theta has to be 1, right? That is the maximum value. So I can say sine omega t in this case has to be 1. So what will be the maximum value of EMF then? E maximum would be equal to NBA omega. This would be its maximum. All right, so see, this is how your EMF is differing. Look, EMF is depending upon the current. Are you getting it? So every time you have the value of the current getting differed. So even if I plot the graph here, look, this is how you will get a graph, okay? Positive part, negative part, and this is showing the maximum value of the EMF over here and minus value. Means at every moment the current and EMF is varying. I'll just repeat what did we discuss over here. N, A, B, omega. Omega is angular velocity, B is the magnetic field, A is the area of the coil, N is the number of turns. Okay. So flux can be written as BA cos theta. Now, the coil is rotating with an angular velocity omega. So if it is rotating with an angular velocity omega, we can say that theta is equal to omega into t. When you put it here, phi is equal to NBA cos omega t. N for the number of turns, omega t for the value of theta. You get EMF as minus d phi over dt. So when you differentiate this term, minus NBA come out because they are the constant. Cos omega t's differential is minus omega sine omega t. So minus minus will be plus, and you are left with NBA omega sine omega t. This is the equation and the value of this EMF. But just to get its maximum value, E max, or this is also written as E naught, that is its peak value or is it its maximum value. This is NBA omega. And that's how we plot its variable graph. This is what? This is the value of EMF when the coil is rotating like this at different angles. Tell me, class, have you understood this? All right. Muniba, tell me one thing then. What is the difference between AC and DC? What have we studied so far? Difference between AC and DC. In
Um,
simple terms, just tell me.
for DC current, the current is always fixed,
Yes.
and for alternating currents, AC, it constantly changes at every
Yes,
point.
it varies. Yes, very good. Zainab, could you just tell me the basic, very basic principle of the AC generator? Yes, Zainab, please unmute yourself and then tell me. Don't type if you're typing. Just tell me roughly. This is not a test. Just for a revision I wanted.
Is based on Faraday's law.
Yes, it is based on Faraday's law. That
Minus d phi by dt.
is what? Minus d phi by dt. That's how you answer. Just take out your notes and look from there. It's okay.
EMI.
EMF. Yes, induced EMF is there in the coil, which is equal to rate of change of magnetic flux. Okay, that's right. Jyobita, just tell me a basic structure of this coil, AC coil. Yes, Jyobita. Did you draw it? Were you there that time in the class? Because I think you got disconnected.
No, I didn't draw it, got disconnected.
You haven't written?
No.
Okay, till where have you written, Jyobita? Yes, tell me till where have you made the notes and written?
The introduction part.
Just the introduction. Okay.
Yeah, ma'am, my
Haven't
mobile charge got off or finished, that's why.
So you haven't written anything about the AC?
No, ma'am, from after 10 minutes I have joined. Till that time I have wrote everything.
Okay, just take the screenshots then because
Okay.
these are important portions. Okay. Jesslyn, just tell me which energy is getting converted here in AC.
Mechanical energy,
Into?
electrical energy.
Very good. Mechanical energy into electrical energy. That's what we did so far. Okay. And this was its basic structure. Now the formula part, this is the flux. This is the EMF because we differentiate the flux and we get the EMF. And this is the maximum value of EMF that is possible. Okay. Now till here, alternating current is clear to all of you, Jesslyn and all.
Yes.
Yes, ma'am.
Okay. Then please start writing from here, class.